Suppose that X is a prime funnel. Now, where is the Hartshorne conjecture for funnels? This was not yet seen, right? So I want to prove. So I continue my proof, but I move.
Here.
Where?
Right inside.
Okay. No, I didn't know this. Yeah, thank you. Perfect. So so now I know that X is a prime funnel. Okay. And I know also HCF holds. Okay. What I want to prove? I want to prove that it is a complete intersection or this exceptional guy, right? Now, I may assume that N is at most 2 times the codimension, because otherwise Hartshorne conjecture applies and it is a complete intersection. I'm finished, right? Okay? So what do I have to prove? I have to prove that either I have the opposite, so it's a complete intersection finished, or in this case, if it is not a complete intersection, I have to find this exceptional fellow, right? It seems an impossible task at first. You say, come on, where is the Grassmannian? Where do you get the Grassmannian? And here comes the Grassmannian in the following way. So let us do something quite curious. So let C be the sectional curve of X. It appeared also yesterday. So this is X intersected with n-1 general hyperplanes. So the sectional curve, right? And denote by G its genus. We saw yesterday that this genus comes from a junction formula, right? So this is given by this formula. Canonical times H n-1 plus n-1 times degree, or if you prefer Hn, right? Right? Now let us look at this more carefully. The canonical is minus index times H, right? Because it is prime funnel. So if I substitute this here, I will get some nice number. So this is minus H times D. This is a degree, of course. So this will be, if I'm not wrong, n-1 minus index. Let us call the index I to shorten things. And here is the degree. Agreed? Clear, right? No? Instead of K, I put minus I times H. So you have a D here, and it's a first kindergarten algebra. Well, my friends, so far so good. Now, what do you know about the genus of a curve of given degree in some projective space? You should know something extremely important, namely that there is a bound on it. And this is a famous Castelnuovo bound for the genus of a curve in Pn in terms of its degree and the dimension of the ambient space. Unfortunately for you young fellows, in Hartshorne's book, it's only for P3. But the proof, if you well, just look in the other monstrous book, Griffiths-Harris, and you'll have the argument. This part, I should be more careful because you are taking pictures of me. I just wanted to say that this part is correct in the Griffiths-Harris book because some other parts are not. So I'm not the first to discover this. it's an excellent book, together with, there are mistakes that are enlightening if you understand them. And especially if you don't code the result exactly. I mean, if you correct it, it's perfect. Okay, so let's apply the Castelnuovo bound, right? And this is kind of ugly, but that's why I wrote this thing, because it's... So first of all, where is this curve? So I was in P capital N, and I have cut n minus 1 times, right? So this curve is in P C minus 1. You agree? Because this is, no, C plus 1, thank you. This is n minus 1, right? And this is n plus C minus n plus 1, and this is C plus 1. Correct. Okay? Okay. And the bound is this horrible thing, m times, I will explain which is m, minus m plus 1 half. I had to look on internet for that, because C plus 1 minus 1. I write it like this just to explain the formula. So here m is the famous integral part, here degree minus 1, and here is the dimension of the ambient space minus 1. That's how the formula, so this is C. Okay? And here it is a dimension of the ambient space minus 1. So I wrote it like this to recognize it easily. So this is, in short, this is m times d minus m plus 1 half times c minus 1. Okay? Hopefully I'm not too wrong. Okay? Now, as usual in Castelnuovo formula, the crucial thing is to know what m is. Okay? So I claim that m is 1. So m is 1. Why is m 1? Well, essentially because on one hand you have that c is bigger or equal than half n. On the other, d, say minus 1, is smaller or equal n minus 2, right? This was my hypothesis, right? So one is smaller than n minus 2, the other is bigger than half n. So when you divide, you can divide, and you get that it is smaller than 2. So hopefully it's correct, right? Okay? Aha! Aha! So this, now it's a beautiful number. It is d minus c minus 1. Right? Right? Ah, good. Good. Very good. Very good. Now, let us come here. And I make the following claim. This guy is 0. This guy is 0. It's a claim. If this guy is 0, so admit the claim. If this guy is 0, then the index is n minus 1. So these are Fano manifolds, prime Fano manifolds, are classified according to the index the higher the index, the simpler the classification. The index can be at most n plus 1. This happens only for projective space exercise. Next case, index equal to n. Only the hyperquadric exercise. Next case, index equal n minus 1. Not exercise. Fujita, 3 papers, Journal Mathematical Society of Japan, 70 pages. Difficult, but we know all of them. And they he called them Del Pezzo manifolds. The 3-dimensional case was known. So 2-dimensional Del Pezzo surfaces, everybody knows. Blow up of at most 8 points in general position, blah, 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 blah. Okay? Next, 3-folds, Fano and Diskovsky. Next, any dimension, Fujita, to be correct. That's how history happens, right? So Fujita classified all of them. So this is Del Pezzo manifold in Fujita terminology. Fujita. And you look at the list and you see that they are easy. They are either 2 or 3 exceptional or complete intersections, namely cubic hypersurface or complete intersection of 2 quadrics, or the Grassmannian of lines in P4, which is the only one having degree 5 and dimension 6, which is exactly on the limit of my bound. And so, if we know the claim, I convinced you that, right? That this follows from that. Now the claim is seen as false. So first of all, assume this number is, say, okay. So assume this is bigger or equal than 1, right? Let's see what we get. Let's see what we get. So we see, we get something like the degree, half the degree. So this will be bigger or equal, right? Then half the degree. Let us call the degree my d, right? Right? So you get, what do you get? You get d smaller or equal. I have to multiply that fellow with 2, right? So 2 times minus 2c minus 2, right? Correct? I computed till d minus c minus 1, and here I have something bigger or equal than half d, if that fellow is at least 1. It's natural number, right? So no problem. Okay? Agreed? But, my friends, d was okay, first you have to do that, and then you get that d is bigger or equal than 2c plus 2, right? But it was smaller or equal than n minus 1. So n is at least 2c plus 3. So Hartshorne conjecture applies. We are in the range of the Hartshorne conjecture. And it's finished. Okay? Questions? So I thought it is instructive to recall Castelnuovo bound, things like this, classification of funnels of high index. Just I made it with this ideological purpose of stimulating the students. It's not that
So from the class result we can get 0, 4.
Exactly. It's the only one from the list which is not a complete intersection and satisfying this condition, of course. And otherwise, dimension, the codimension is very small. So, since it is already prime funnel, Hartshorne conjecture applies for Fanos. So that's how you show. So be careful. You show that this nice bound follows from Hartshorne conjecture for Fanos. More than that, for the moment, I cannot do. But be my guest if you want to. If you want a piece of cake. Questions?
Your expectation for will be proved
If
something.
expectation 4 is this one.
4.
Yes, this one. This is expectation 4. No.
Or
Excuse me. So, what was expectation 4? Because I don't remember how I made numerotation. Let me see. Come on, where are you? This was expectation 3. So I was wrong here. Excuse me.
No, you are.
No? No.
You're fine.
I have changed the order because this was for yesterday, so it was 3. Yeah, it's okay. It's okay. Expectation 4 is this one. Yeah, this is 4, and 3 was Hartshorne conjecture for Fanos. So it's okay.
So is there some
That's
partial
exactly.
result about this
Sorry?
expectation? Is there some for special case or some partial result for this?
This? I mean, it's the best possible result, and it would follow from the Hartshorne conjecture for Fanos. So it's enough for me to believe into it. I mean, but of course one can try to prove it directly. Exactly. That's the point. Absolutely.
You can give me hint.
Nah. I would have published it. No. It's non-trivial because if you learn, if you look at Barth's proof, it's quite involved. It's the subject of an invited address to an ICM. I mean, and it is ugly with half d times d minus 5. I mean, but this should be the correct bound. And I am more inclined to work to try to prove the Hartshorne conjecture for Fanos. This, I think, is a very good problem. Hard. But this would be absolutely a breakthrough. I mean, it will give some consistency.
Can be also divided into the Fano index or not?
Good question. The higher the index, the easier the proof. Tomorrow, not tomorrow, the day after tomorrow, you'll hear about some other cases where it is proved and where the index is high. Essentially bigger or equal than half dimension plus 1. So then, no, it's fine for interesting cases, namely for local quadratic entry varieties and for dual defective varieties, which actually will be the subject of the next lesson. So you'll see that these Fanos of high index are really the heart of this yeah, the heart, the core of the story.
The Fano index is lower, smaller.
Yes. If the index is small, even the classification is completely, I mean, it's kind of hopeless in any dimension. Because the point here is that I'm not speaking about surfaces or 3-folds or 4-folds, right? I'm speaking about any dimension. And,
but in one always assume Fano index is 1.
you can assume, yes, but this is a hard case. I mean, you assume the index is 1 because you cut by hyperplanes. You can assume, because if you cut, that's easy to see. If you have a manifold and some hyperplane section of it is a complete intersection, then X is a complete intersection. So cutting, the index decreases by 1. So you can assume index 1, but you are not interested in doing so, because the higher the index, the easier the problem. When the index is 1, is the most difficult case. So this is, I don't think this is how you should proceed. Yeah. Yeah. So evidence supporting Hanno conjecture for Fanos can be seen as coming from the following directions. First of all, codimension-2, which is completely open for the general Hartshorne conjecture. Second, our result, quadratic, which is something. Third, many cases interesting and those appearing in nature, so to say, when the index is high. So these three cases, which are different in nature somehow, make me believe that for Fanos it should hold. Yeah, and this is okay. I proceed. Don't even imagine that I'm finished. I still have a long way to do. Well, I promised you some argument about the quadratic case, right? My problem here is that there are many things that have to be recalled, and I have to be kind of reasonable, not to overwhelm people. So some of them will be proved, some of them will be, I don't know, admitted. So maybe let me do something that is kind of easier instead, because I'm also looking at my watch, and you look much less sleepy than last time. Maybe the sleepy guys already went to sleep. So the remaining ones are, you look not as energetic as myself, of course. That's difficult, but you look quite well. So, you know that in order that a speaker be in shape, he needs some intelligent eyes looking towards him. Yes, yes, yes. If instead he's saying like this, heads falling down, then that kind of interrupts the flux of energy from the speaker, right? So I feel very well. So I can continue for some 1 hour and a half. Is okay?
Yes.
Any complaints? No, I'm joking. Half an hour, huh? Okay. So
10 minutes.
Sorry?
So 10 minutes you already spent 1 hour and a half.
I know.
Yeah.
That's why I said 1 hour and a half still, just to see how many people are falling down and say, okay. So I want to present, instead of giving that thing, because there are some complicated things about, not complicated, but I have to introduce a second fundamental form and to make a whole speech about it. If it is less popular, so I'm afraid the students don't know about the second fundamental form. They know from the course of differential geometry, and it's very related, but it's algebraic geometry, geometric differential form. So so instead, let me give you, because here you will have enough ideas, I think, another expectation that is very nice and follows from the Hartshorne conjecture, not for Fanos this time. So expectation, help me with the number 5, I think, right? Okay. This is again from myself and Rousseau, the last paper we wrote. It confirms something that experimentally has been noticed from some time, and namely that prime Fanos of high index should be complete intersections. the point is to define what high index means. Okay, so to give a precise bound, right? So Fanos prime, sorry. And the expectation, so X prime Fano, index at least, the expectation actually gives you the exact bound. It is 2 times n plus 5 divided by 3. Then X complete intersection. And what I want to show is that it follows from Hartshorne conjecture. Actually, it follows from Hartshorne conjecture for Fanos and Hartshorne conjecture for something very special. So from less than the full Hartshorne conjecture, right? And this is extremely plausible. Let me tell you why. Because Fanos of arbitrary dimension have been classified up to now in these cases, the first 2 being trivial, index maximum, n plus 1, only projective space. Index n, next to maximum, hyperquadric. Index n minus 1, del pezzo, Fujita. And last, index n minus 2, Mukai. Difficult, important work. We had an invited address for that. I mean, something really excellent work. Okay? And the bound holds. So you see, if I put here, for instance, n minus 2, right? I do the computation, and it should be a complete intersection when n becomes large enough. And if you look at Mukai's classification, that's excellent. Exactly as it should be. Okay? So this is something we expect to hold. And now I have to convince you that this follows from the Hartshorne conjecture. And the proof, I think, is very instructive, because it involves a lot of things that you don't expect, maybe. Okay, so let's see. So so proof. The first thing is, if the index is at least n plus 1 half, so a fortiori here, then X is covered by lines in the sense of the previous. This is non-trivial. It follows from Mori's work. Maybe I will skip that, because referring to the Mori work when he, in that famous paper when he proved the Hartshorne conjecture, the other Hartshorne, this is amazing. So the main tool in everything we did, in particular in my work with Francesco, but not only in our work, in many people's work, was Mori theory. Now, Mori theory started by his attempt and success in proving the other famous Hartshorne conjecture, that is, the only manifold, projective manifold with ample tangent bundle is projective space. And this work turned out to be quite useful, it seems, in proving, in attacking the other Hartshorne conjecture. Master Hartshorne would have remained in history if only he had proposed these 2 conjectures, because they were extremely stimulating. So this is full clear, right? Good. So believe me that this holds, because the proof is kind of, it comes from, for instance, unique characteristic P methods and Frobenius, and so it's not the moment to speak about that, believe me. So this is first step, so maybe step 1. Okay. denote something about by A, something about the formation theory of rational curves. So denote by A the dimension of Lx, where Lx is a variety of all lines through X. Lines L, X on L, and containing X. So I said that it is covered by lines. Okay, so through each point there is a line. Okay, now, so I would use this notation when X is a general point of X. Okay, now the formation theory, see books, there are two of them, either by the bar or by Kolar. This is kind of encyclopedic, this is kind of introduction, so you should begin with this one. Higher dimensional geometry, right? It's a Springer University text, and this is Grundlagen, which already should explain that this is not so easy to read. Okay. So deformation theory shows something very interesting. So first of all, this variety of lines passing through a fixed point is naturally embedded in some n-1 dimensional projective space, which is exactly the space of tangent directions at X. So these are lines contained in X, right? So they may be naturally seen, right, as contained in the tangent space at X. So they can be seen as points in the directions here. So this Pn-1 is a classical projective space associated to the projective space, tangent space at X. Okay? So far so good. But now some very nice properties happen, namely, so properties of this embedding. Some are trivial, some are deep. Trivial. So Lx is smooth. This comes from deformation theory. Essentially because passing through a general point makes the normal bundle to be, in its Grothendieck decomposition, made only of zeros and ones. So it is not obstructed. The H1 vanishes, and by the general theory of Hilbert's scheme, this means the point is smooth on that scheme. And that's why it is smooth. So this is smooth. This is not complicated. What is non-trivial is the following. If, moreover, A is at least n-1 half, then Lx is irreducible and non-degenerate. Now, irreducible I can explain. Proof. Assume it is reducible. There are at least two components. The dimension is the same. But this is half the dimension of the projective space. So they meet by fundamental theorem of projective geometry. But this produces singularities. And I previously stated that it is smooth. Okay, so this is easy. Next, non-degenerate. This is something that I like enormously. And this was the first instance I started admiring a Korean mathematician, because I already admired Chang-um Jumong, Quinn, Sandok, and others, because this is a splendid and extremely useful result by Huang, which is completely non-trivial. So you see, you have to use things. I mean, it's not gratis. It is very interesting because being non-degenerate usually is gratis. If you have a variety which is degenerate, just take that hyperplane and decrease the dimension of the ambient, right? But here you cannot do that because you are in the projective, in the space of tangent directions. So that space is fixed. You cannot modify it, right? So the fact that it is non-degenerate is crucial. And this is an argument with coming from differential geometry with foliations, and very nice, splendid. I can give references to people that are interested. Okay, so now we see that under this assumption, things behave very well. Now, I claim that this assumption is true here because claim the index is just this number plus 2. This is a junction formula. Once you know that this dimension, this A, happens to be just the degree of the normal bundle of a line in X, L, general line. And the fact that this is the degree of the normal bundle, because I defined A to be the dimension of this variety, right? This comes from deformation theory. So you know, when deformations are non-obstructed, and I explained a little bit that the H1 is 0 because the normal bundle is made of positive elements, the dimension of the variety is just H0. And the normal bundle, just to explain, is in its Grothendieck decomposition, as I told you, made only of ones and zero. So its degree is the number of ones. It is A, right? So A was defined to be where is the definition? A is a dimension. I wrote it somewhere, but I'm unable to. Where is it? Can you show me? Here, yeah, okay, excuse me. Okay, so the point is that deformation theory tells you that this A is nothing but the degree of the normal bundle.
On the general line.
Yeah, on a general line. The point is that because the line is general, the normal bundle is positive in this sense. This is the first point. The second point is then the H1 will be 0, right? So this is for a general line. If you want it to pass through a point, you have to twist by O of -1, right? Because you are on P1 and you fix it, you fix the point. So the ideal sheaf of the point is O of -1, right? So you write here -1, -1, and here 0, 0, 0, 0, right? So what is H0 of NL of -1? H0 is the number of ones here, that is this A. But H1, H0 of NLX of -1 is, by deformation theory, is exactly the dimension of Lx. And that's the proof, essentially. Okay? Good. And why is this a junction formula? Well, remember, what was the index? The index was essentially this, minus k times L, right? because minus k is I times hyperplane section, and hyperplane section L is 1 because it is a line, right? So you have this, okay? On one hand. On the other, by adjunction formula, this is the degree of the normal bundle of L plus 2, right? The 2 comes from the anti-canonical bundle of P1, right? Right? But this is so what is this? K P1, the line that is KP, right? Plus that normal bond, right? Kx, excuse me. Okay? And this is minus 2, right? Well, degree. The degree is minus 2, right? So this is, this k, well, I have to change signs. So this is 2 plus the degree of the normal bond. Okay? Adjunction formula. Nothing else. So the hypothesis was, so I at least 2n plus 5 over 3 is the same as A at least I have to subtract 2, right? So what do I get? 2n minus 1 over 3, right? And this is bigger or equal to n minus 1, obviously. Okay? So this condition, first of all, ensures on one hand that I have lines passing through each point, and secondly, that they are well behaved, in the sense that their variety regarded inside the space of tangent directions has all good properties you may expect. Smooth, irreducible, non-degenerate. Okay? So you can combine various things. Good. And now, let us translate this condition with A. So this can be written as follows. Let us see if it is okay. So let us compute. So minus 2, this will give you 3a, 2n minus 2 plus 1, 2n minus 1. Correct. Right? Now what is this? Ha! What is this, my friends? A was the dimension. Now I look at this small object. This small object will have the property, and this will be a main theme in the 2 remaining lectures. This small object has a tendency of describing the big object. It's like a drop of ocean that reminds you about the ocean. Now I am preaching Buddhism. Okay, so this is what? Dimension bigger or equal 2 times codimension plus 1. So this is exactly the Hartshorne condition, the very small codimension, for the variety of lines. That's why I was interested that this object be smooth, irreducible, non-degenerate, because otherwise these statements are meaningless. You follow? So at this point, I apply the Hartshorne conjecture, but for lines, not the general one. So, by the Hartshorne conjecture for lines, it follows that my Lx inside Pn minus 1 is a complete intersection. Okay? Ha! So what? Then some other miracle happens. I finish in a few minutes. Now, I have a lemma. whose proof is very beautiful, and you will see probably tomorrow. So assume that x, not x, because I will apply this for Lx. So put some other letter, y. So assume that y in some p, say r, is a complete intersection, and its dimension is at least codimension -1 this time. So it is small codimension, but not so small. Okay? Then something great happens. The second variety fills up the whole variety. Now, are you familiar with the second variety? Should I explain this? Or if not, I will start with the second variety and properties, and I will prove this lemma in the next lesson. In the meantime, you study the second variety. Okay, to be prepared. So this is the first thing I need, and then let me observe that here I have this condition which is stronger than that. So apply lemma, let us call it lemma 1. Apply lemma 1 to Lx okay. I need a condition of this type, but I have much more, right? So okay, it is a complete intersection, we just saw it. It satisfies this, so it follows that the second variety of Lx is the whole p n minus 1. Okay? The second variety is the locus, geometric locus of all seconds and tangents, right? So you have a variety embedded. For each pair of points, possibly coinciding, you take the line determinants. If they coincide, you take the tangent, right? And that's the second variety. That's the definition. Okay? We shall study the second variety in the next lecture seriously. And now, lemma 2. Lemma 2 is a famous paper by Huang and Quebecus in Krelle, 20 pages paper, in which they prove something more general than this. They work not for prime Fanos, but for Fanos with cyclic Picard group, but not necessarily generated by the hyperplane section. Okay? And this makes the proof terribly complicated. But I need their theorem only for lines. And here I have a proof, 5 lines, that will be presented in the next talk, saying something very beautiful. Namely, if this happens, so you have a manifold covered by lines, and you know that the second variety to the variety of lines fills up the whole projective space of tangent directions. Then X is conic-connected. It is for any general points exists a conic contained in X and containing the points. Conic. Of course, the original. No, the X. No, the original X. Yeah. Of course, the original X. Okay?
The T suggests plane conic.
Sorry?
What is conic?
you have to prove this. I mean, that's highly non-trivial. In particular, it is rationally connected. So any two points can be joined by a rational curve because a conic is a rational curve.
Plain
Yeah.
conic,
Conic. Plain conic. Yes, usual conic. What kind of well, conics are plain? Okay? You will see the proof of lemma 1, lemma 2 in the next lecture. Now, how can we finish our thing? Well, so from lemma 2, we deduce, and this will be lemma 3, but I don't want you to kill me instantly, that Lx is contained in C quadrix. C is a codimension. So here I have to explain you how.
Lx is contained in the quadric.
In C quadrix inside, exactly, inside Pn minus 1.
What does it mean, C?
C is a codimension. I keep the notation. C was a codimension of X in, so I started, this is a long argument. Okay. Okay. This has to be explained, and I will. But now, this C, so remember, it is non-degenerate. It is a complete intersection. And it is contained in C independent, it was understood, my baby, linearly independent quadrix, right? For a complete intersection, this can happen only if the quadrics are among the equations because of degree, right? So they have to be among the equations defining the variety, which is a complete intersection. You understand? Because what degree can you have? One, not, because it is non-degenerate, right? But if you don't have degree 2, then there are no quadrics containing the complete intersection. You understand? Because those degrees are minimal. So any quadric which appears among the equations. So how many quadrics can you have? At most, the number of equations. But the number of the equations is a codimension of Lx inside Pn minus 1. Aha! So from here, we get the crucial thing, namely that the number of the quadrics is at most the codimension n minus 1 minus a, right? A was the dimension of Lx, n minus 1 was the dimension of the ambient space, right? And we get this. Yes! But now, my friends, this is more or equal. If you look, A was terribly big, was 2n minus 1 over 3, right, at least. So this is certainly smaller equal than I write something quick, then, and it is, you can put something even bigger here, right, because of that. But this is enough. And now, what do you get? And now the Hartshorne conjecture for funnels applies, right? And we get that X itself is a complete intersection, which was the conclusion we were seeking for.
Lx is funnel?
No. Yes, it is funnel, but remember, I already explained this. So, where are you? Prime funnel, right? Prime funnel of high index, complete intersection. What I used? I used two things. Hartshorne conjecture, 4 lines, No. For the variety of lines inside Pn minus 1, for this Lx, which is a very special situation, it's not the general Hartree conjecture. Right? It's not for Fano because I don't know to prove that Lx is Fano. Otherwise, it would have been a consequence of expectation 3, right? So I need some more refined form of Hartree conjecture, but a very special case for lines and for Fanos at the end. And so that's how.
Small x is general in x, right?
Who? Small x is general, yes, and it's enough. You see, it's enough to work with a variety of lines at a general type to obtain the conclusion.
So we're using Hartree conjecture assumption twice here and
Exactly.
diagonally. Okay.
Exactly. Once for Fanos at the end, and once for lines here. So actually I use less than the full Hartree conjecture. And this is a last instance where we see some nice conclusions that can be. And here all steps are nice. So I hope you will appreciate the proof of both lemma 1 and lemma 2. And this remaining thing that was here, this kind of, let us call it lemma 3, because otherwise I will forget that this will be lemma 3. Actually, this is the point I wanted to avoid, because here somehow the second fundamental form enters into the game. I cannot avoid it. Thank you.
As I mentioned before, if you have a question,